Good morning. So, since we're only planning to do two sections this week, I used the word only. One of those sections has quite a bit of material, but I thought we'd take maybe 10 minutes or whatever to talk about L'Hopital's rule and products. And I'm not dwelling on this material because it's much more specialized than what we saw yesterday. But in theory, you can sometimes use L'Hopital's rule to evaluate products. Indeterminate products are things like, I say things like, they are limits where you have 0 times infinity, because the infinity is trying to make the product big, and the 0 is trying to make the product equal to 0. And hypothetically, you can always rewrite a product as a quotient and then try to use L'Hopital's rule for quotients. If you do this rewriting, it will be an indeterminate quotient. In reality, this is very limited, and it's very limited because usually 1 over g of x is going to be a more complicated function than g of x, and it's just going to kind of get worse as you take derivatives instead of better. And I think the main application of L'Hopital's rule and products shows up when you have natural logarithms and power functions, because the derivative of a power function is a power function, and 1 divided by a power function is still a power function, and the derivative of the natural log is a power function. So you have a bunch of power functions, and they're relatively easy or straightforward to deal with. Something like the limit as x goes to 0, the natural log of x, skipping ahead a bit, of the square root of x times the natural log of x. And as x goes to 0, the square root of 0 certainly equals 0. As for the natural log, it has a vertical asymptote at 0. It goes down to negative infinity. So this is a 0 divided by infinity limit, and if 0 times infinity limit. And if your goal is to try to use L'Hopital's rule, there are always 2 ways you could rewrite it. But even in a best case scenario, usually only one of them is going to work. You could do this. That's certainly a valid way of rewriting it. But if you now start taking derivatives, this is just going to get messier and messier. In particular, one over the natural log is the natural log to the negative first. So if you take the derivative you have to use the chain rule. You've got that natural log as an inside function, and the derivative ends up being this. And now you say, well, that's worse than what we started with. So that's not a good idea. I mean, you're not doing anything mathematically incorrect, but you're not going to get to the right answer this way. Whereas this works out smoothly. And it works out smoothly in the sense that, you know, when you take this derivative, it does arguably get a little more complicated. But when you take the derivative of the natural log, it gets so much simpler that it more than counterbalances that. I mean, let's see what happens here. 1 over the square root of x is x to the negative 1/2. And you start taking derivatives. And again, just to emphasize, this is indeterminate. 1 over the square root of x is now going to negative infinity as x approaches 0, because it's 1 over 0. 1 over 0 is infinity. And the natural log was already going to negative infinity. So this is indeterminate. L'Hopital's rule is appropriate. And as I suggested, this is good. I don't know what it is. I normally so diligent. I always write the plus C's when I take the integrals and never leave anything out. But writing these limits when I'm doing L'Hopital's rule is just a curse somehow. I was saying that that this denominator, you know, is certainly a little messier than we started with. But now that top is a power function and that bottom is a power function, and we can rewrite it, hopefully without a lot of issue. We can write this as a single fraction, and then we can multiply by 2x to the 3/2. And that will be, I guess if we wanted to, we could just go the full distance and multiply by negative 2x to the 3/2, just completely get rid of the denominator. And we then get negative 2x to the 3/2 over x to the first. And sometimes calculus is testing algebra more than anything else. Hopefully we remember that if we have a power of x in the top and the bottom, we subtract them. So 3/2 minus 2/2 is 1/2, and this is then equal to 0. We can use continuity. We can just plug 0 in now and get the limit. And let's take a look. I never proved L'Hopital's rule or even really gave an argument for it, but it's given us the answer we expect from the graphs every time so far. Let's see. The square root of x times the natural log of x. What happens as we approach 0? Well, you see exactly what we let me make this maybe a little thicker so it can be easier seen from back in the back row. You know, it does indeed, as we approach 0, it goes down for a while, but then it does come back up, and our Desmos starts doing rounding errors a little earlier than I ordinarily expect. But if we just look at the graph, we can see it's approaching the origin. Y is approaching 0. And I mean, you could do the same trick if instead of the square root of x, you had x or x squared, or is there? Here's a situation where we could use the same trick, but this time the limit wouldn't exist. So it's pretty specialized. I mean, I'm not saying that this LNX is literally the only situation it works in, but there's a reason that quotients get a full lesson, and this sort of gets 15 minutes at the beginning of a different topic. So, in fact, why don't I, just for online students, why don't I split this video into 2?